Okay, let's get started. Welcome back to Object-Oriented Programming in Java. So, what you're looking at in front here on the screen is the midterm exam. We're about midway through the course. It doesn't feel like it, but we are actually about midway or approaching the midpoint in the course. So it's not a bad idea to start thinking about the midterm exam. It is a take-home exam. In fact, you're looking at it right here. It can be obtained from right here in the Object-Oriented Programming with Java. It's the same midterm for the weekend versus the weekday section. All the materials are the same. So here's the exam right here. It's a take-home. It needs to be done and uploaded into the EMS. It cannot be submitted via email. The EMS is not ready yet. So I just looked at it a few minutes ago and it appears to be empty so far. So perhaps in the next week or so it will become available. So save your work up if you're doing it right now. So about right now in the course is when you should start thinking about the midterm. Here's the midterm. Let me explain a couple of things to you, just so you have some guidelines to fill it out. You're going to answer all of the questions in the midterm. It's worth a total of 25 points. So 15 points in the beginning here. You don't need to provide source code examples, and a sentence or so, or a few words actually, is okay. You don't have to write long answers to these questions. As an example, describing the 4 main characteristics of object-oriented design, a PI, which I gave to you, so that stands for abstraction, polymorphism, inheritance, and encapsulation. What is an interface? Interface method. What is a class method? Instance method. Excuse me, not interface. I got interface on the mind because I'm going to be talking about interfaces today. Instance method, overloading, overriding, use some basic terminology. So 1 or 2 sentences or a sentence, a couple words will suffice. You can download this, put a couple lines in here, and then write your answer right here, and then, submit it as a document. The next section, section 2, you answer the following question with Java source code. So first section is just words. The second one, you're going to provide some examples. So you're going to show a Java source code how to inherit one class from another. We talked about inheritance last time. So one class is going to extend another class. We're going to look at how to use an interface class today. So you'll have to wait till today's lecture to learn about interface classes if you don't know about them yet. And then pretty much after today, we're at the midpoint, I would say. So we've covered all the material that you would need to do for this particular midterm. These don't have to be fully running programs that you're writing. You can write source code snippets, source code pieces. You can put all this stuff into one program if you want and give me a program. Or you can simply just write the code. It doesn't have to be compilable code. Show how to source code, how to create a subclass, overload a constructor and a superclass. You're going to need to have both a sub and a superclass, obviously, to do that. So you can combine pieces if you want. Write one thing that does all of this stuff if you want. So your choice on number 1 through 4. Just implement the behavior that it's being requested in some sort of a Java source code example. In section number 3, we have miscellaneous Java concept questions, where you're looking at code and you're answering questions about the code. And you want to know precisely, for the example for the first question is, what is going to be the outcome or the output of this Java program? And then basically what you're going to do is not have to actually read it if you don't want to. You can cut and paste these examples, stick them into a file, compile them. All of these source code things should compile just fine. So you can cut and paste this and see what the outcome is, or you can predict the outcome. As the instructions say, you can cut and paste the code, compile it, run it, see what the output is, and then explain why it's happening that particular way. Why the output is producing what it's producing. And the trick is down here, actually. 2 objects of the same child inside of the main. So the next one, you can also assume that the weather class is stored in a file called weather.java. You can actually cut and paste it, put it into weather class. Problem2 class is stored in a file called problem2. And here it is right here. You can put it all in one file if you want. What you're going to essentially do is look at this again and basically go through the same concept. Source code compiles and runs. So compile it and run it if you'd like, and then answer some questions. What is the output produced by executing the following code segment? What's the output produced by this? You might have to make some changes in it. You could cut and paste these particular items, put it in the source code. Or if you want to do it without doing that, you can also just answer it on your own without you seeing it done programmatically. In some cases in which you're looking at this stuff, you might have to reproduce parts of the program. If you're given a piece of source code and ask, well, what does this do? You might actually have to create the background stuff to make it work. So if it's not given to you already. So in here I believe you're given problem 2, and that's the driver program for this other class, weather class. And the output produced here, you might have to put that into the code is what I'm saying. It might not already be in the code. So, but you don't have to show me any of the code that you've created. All you do is answering the questions. In the third part, it's kind of interesting. You're identifying the classes and following through a description of a refrigerator. And you're going to list at least one responsibility for each one of the classes. You do not need to create the classes in Java. You don't have to write source code for the third one. You're just describing in words or in a way that any way that you want a set of classes that you would create by looking at the description below. So you read the description of the problem, and you can use any format that you want. You do not have to use UML for this. But if you're familiar with UML, you can create a UML class diagram if you want, if you're familiar with it. Or you can fake it and try a UML class diagram if you want. I'm not grading you on your diagram. I'm grading you on the classes that you have selected to implement. So you can simply list them out if you'd like. And list out, if I were to write this program, how would I design it, is really the question that's going on. Although, if you don't know about UML and you want to learn, want to practice with it, see if you can put together a UML diagram if you want. So, some of you have taken maybe the software engineering course, have heard of UML. If so, then this is your opportunity to practice those skills. And the midterm is due anytime before the end of the course, which is in the end of November. So if this is October, September, October, November, well, yeah, it's about halfway point. Another week it'll be halfway point, in the middle of October. So, questions about the midterm? Not due till the end of the course. Can't even upload it, but you don't want to wait till the last day of the course to do all this stuff. So, about time. We've learned all the material that's necessary for the midterm, so it's a good time to start thinking about it. All right, and if you've missed any of the class meetings and you want to get some of the information for the midterm, you can look at the class recordings as well if you haven't been following along. But most of you guys who are sitting here are the regulars, so you have been here. So don't have to worry about you. It's everybody else who's listening to this recording who hasn't been here for the entire term, who's going midterm. Midterm? Anyway, final exam is an in-class exam, so you have to. Everybody will have to come to campus for that one. So. But I will tell you before what to study, so you'll know what to do. So the topic for today, on the menu for today, is interface design, lecture number 5. So, what is an interface? It's not a class, it's an interface. So we create an interface. So an interface, well, what is it then? Well, it's a way to describe what classes should do without specifying how they should do it. Interesting. It's not a class, but a set of requirements for classes that you want to conform to the interface. So we have public interface comparable. So instead of saying public class comparable, we're saying public interface. So we're not creating a class, we're creating an interface. It goes in a separate file called comparable.java. And this particular one here, this requires that any class that's implementing the comparable interface contains a compare to method. Here's the method right here. And we've put this in here, an object, a generic object, other object. And it's in a method that we have defined as a method prototype that we haven't given a body for. We haven't implemented it. And notice we haven't actually said that it was abstract either. But doesn't it look kind of abstract to you? Doesn't it look like abstract classes? I've covered abstract classes in this class, right? Okay, good. An interface, you might say, is another way of creating an abstract class. And most people go, well, then why not just create an abstract class? If that's the case, why make an interface? I can tell you real quickly why interfaces are good. And I have to compare Java with C++. In C++, we have multiple inheritance. We can take one class and inherit it from as many classes as we want, which is nice. We just separate them by commas. We go, actually we say like, public rectangle, and we put two you don't have to worry about this, but you put two semicolons in there, you put a semicolon in there, and you go public object, comma, square, comma, rectangle, whatever happens to be. And you can actually extend, which is the Java keyword for a class, but you can extend, inherit, however you want to describe it, multiple classes. In Java, you can only extend one class. It doesn't actually support multiple inheritance. And you could possibly imagine, you could probably think, well, why didn't they do that then? Well, the interesting thing is, if you follow along with the inheritance concept, you're really only going to implement multiple classes in one class if it applies. So in C++, going back to that as an example, let's say we want to inherit, we have shape, that's the base class, and we want to make a rectangle. We can inherit from shape, and then we can inherit from, let's say, toString, another class we created that prints out the shape. What we're actually doing is taking in that toString class as an example, or let's say printMe class, that has a toString method in there that prints out the shape. And a rectangle is going to be printed out different from a circle, or different from a triangle, or different from other shapes that we might inherit from shape. So what we're really doing is extending the behavior of that print, including the method toString to print it out, but we're going to have to override it. So in C++, we can create, pretty sophisticated classes and then just override it. But in concept, is it really necessary to actually implement those classes and inherit from those classes when, in fact, all you want is going to be a method to toString, because you're going to want to print out the shape? So in Java, the approach is, well, implement an interface. So we can implement as many interfaces as we want. We can only inherit from one class, but we can include interfaces as well. So we extend, if we were writing this in Java, we would say, that our new class rectangle extends shape, and it implements toString, or whatever we call printMe, or whatever we called that other class. But instead of creating a class out of it, we create an interface out of it. An interface gives us the blueprint for the functionality that we should implement in that object. But instead of overwriting it, we're just writing it for the first time for that object. Saying the toString method should be able to print it out, or something, which is basically all the functionality that a toString, to take some data, bring it to a string so it can be printed out onto the screen or something. So it's really the same concept, but in true object orientation. Back in the beginning, the concept was a single line inheritance. So C++ sort of, it doesn't really break the rules, but it makes it more possible for the programmer to make some abnormal looking classes. As an example, in C++, if you wanted to, you could take shape as a base class, create a superclass, call it rectangle, and then instead of just inheriting from shape, you can inherit from car and bus and train and all these other classes that make absolutely no sense for a rectangle. But it's legal in the language, and C++ allows you to do that. And then you have all these methods and all this stuff that doesn't really apply towards this object, and you've really made up a pretty screwed up object in the end. One of the things with Java is it kind of corrected all of the mistakes that could possibly be made in C++ and said, you're only going to inherit from one class, but you can implement the behavior for many different interfaces. So we know you want the functionality, but we're not going to allow you to put something in a rectangle that doesn't belong in a rectangle. And a rectangle comes from shape. And then if you want to do like shape and then rectangle and then do something else from rectangle, that's fine. but you're not going to be able to take in circle and square and all these other things. Well, square maybe from rectangle, but anyway, all these other things that come in, into place. So it's kind of the same concept of multiple inheritance, long story short, but it's through interfaces. Instead of calling it a class, we're calling it an interface, which is the logic. So in terms of our interface declaration, we're using the keyword interface. So the declaration consists of the keyword interface, its name, and the members. Similar to classes, interfaces can have 3 types of members. It can have data members, member functions, and then nested classes and nested interfaces. Really haven't looked at nested stuff. We'll probably look at that in the last week of the class. But in a nutshell, if Rectangle wanted to create its own object that was... let's say we didn't implement the toString, we didn't implement the printMe object. Instead, we put an object inside of Rectangle that said printMe, created another class in there. We could nest another class that works with the Rectangle object, that its job is to print the rectangle to the screen. If we wanted to, we could nest that inside. And what this slide is basically telling you is you can nest interfaces and you can nest classes, you can create methods, and you can have data inside of this interface, just as if it were a regular old class. And it actually, outside of the implementation, it is a regular old class. But it's called an interface because it's an empty class. It's a class, an interface is designed to be implemented. So it shouldn't have any method bodies for anything. So in theory, it's abstract. But we can leave out abstract. So instead of having to type the word abstract all over the place, we could just leave it out and call it an interface. If it's an abstract class, we can't inherit it. If we were creating rectangle and it was extending shape, we can't extend this class as well. So we make it an interface, and then we go, okay, implement this interface, implement that interface, put in as many interfaces as you want. So you'll find that you'll end up creating interfaces instead of abstract classes when you want to facilitate multiple inheritance in a lot of ways. So, interface members. So the interface can define named constants, which are public, static, and final. Named constants. In an interface, when we declare data, we're declaring named constants, which are values that don't change, which are used in the interface. Outside of that, there should not. You don't want to have variables in the interface because those data members actually belong in the class and not the interface. These modifiers are omitted, so we don't have to put static, public, static, final in front of anything. We just go integer silent, integer terse, integer normal. And it's kind of common in Java as well as C++ for named constants to be in all capital letters. It's like, float or double pi equals 3.14. We're not going to change the definition of pi, and we're going to put the pi in capital letters. When we see pi, we go, oh, that's a named constant, which means it's a constant variable, doesn't change. We can't change the concept of pi. It's going to be that number whether we want it or not. So automatically, we can leave out everything because it's assumed. Interfaces never contain instant fields. They can't. There's nothing for each. You can't make an instance of an interface. So why should you have instance data members? Doesn't work that way. So interfaces are implemented by classes. They're not classes. So by default, everything's static. Everything's public because we have to extend it. And if it's not something we can make an instance of, then classes can see it, but the driver program can't see it. So we can leave it as public. We don't have to go private or protected on it because by default it's for the class implementation. Static because we don't make instances. We're working at class level variables, which is what the keyword static is. Final means it doesn't change. It's constantly that value. It's named constant. And you're wondering, well, why is that so restrictive? Because this isn't meant to be implemented. You don't implement in the interface. You set a template that's going to be implemented elsewhere. So you can set these variables that are going to be used in the methods that are going to be implemented for this particular interface. So, All of the name constants must be initialized. Can you imagine why? You can't initialize them if you don't put them in the... If you got a value that can't change and you go integer silent, and you have not assigned it a value, you're never going to be able to assign it a value. This is a final value. So you have to initialize it with a value. Otherwise, outside of this interface, you can't initialize it. It doesn't change. It's like saying, you know, double pi, but never defining pi as 3.14, whatever it is. I don't even know what pi is right now. I think it's, if I remember, 3.14 or something. I guess I should look up my references when I start to use examples. It's been years. Okay, so I get set verbosity. It's going to set one of those levels. It's going to take in one of these levels here as an integer value. And these are function prototypes. These are methods. Method prototypes, not implemented, just like your abstract methods that we looked at. So the methods, they're implicitly abstract. We don't have to put the word abstract there. They are omitted by convention. So every method declaration consists of a method header and a semicolon. And what do we have here? This is the method header. Semicolon at the end. So used to call them footprints. No. What's the word for it? The method header was not a footprint. I'm thinking of another. The word will come to me in a few minutes. It's like blueprint, not a blueprint, not a footprint. Oh well, forget it. It's just the layout where it has a certain number of parameters are identified, and we can have many different headers that have a different number of parameters. Oh, it's on the tip of my tongue. Signature! That's what I wanted to say. It's the signature of the method. The method signatures, which is the header, or the first line of the method. Signature. Now I'm never going to forget that one. They're implicitly public as well. They're omitted by convention. We don't have to put public abstract on anything. No other types of access modifiers are allowed. And they can't be final nor static because they're meant to be implemented. So they're meant to be implemented in classes that are going to create instances that are going to be able to use these particular interfaces. Modifiers for interfaces itself. So for the interface itself, an interface can have different modifiers. It could be public, package, or abstract. All interfaces are implicitly abstract. Anything abstract you can't make an instance of. So an interface would be an abstract access for the concept of the interface. And it's also omitted by convention. And it's also seen in the package level as well. So, to implement the interface in a class, 2 steps to make the class implement an interface. Here we go. We declare that the class intends to implement the given interface by using implements. So class employee implements comparable. And then we have the rest of the class body that follows it. Or supply definitions for all of the methods in the interface. Not an or. You supply all the definitions for all of the methods in the interface. So we have here, this is our interface. This is in the interface. We have in the class, we're going to implement the method that's in the interface as compared to. And this is from the template we saw in the previous slide. The compare to method is going to say employee other is equal to employee object. Create another object, compare 2 objects to see if the salary is higher or lower between the 2 objects. So we're comparing employees by their salary, essentially. And we're saying which one is higher or lower. So note in the comparable interface declaration, the method compare to is public, but the modifier is omitted. We haven't, this is back here actually. Compare to, this is the interface we're using in an employee class. It's nothing here, it just says integer. It doesn't say public, it doesn't say abstract next to it. So in the implementation of the employee class design, you cannot omit the public modifier in the employee class design. So we have public integer compare to. This is where this public is coming from. So in the interface, we said integer compare to. In the implementation in the class employee that we're using the this method and we're going to implement the method, then we've given it the class modifier public. If we leave it out, it's going to be private, because everything by default is private. If we put it in, we have to make it public. So we have to include the word public if we want to make it a public, although it came in public in the interface, if that makes any sense. So let's see. Otherwise, it will be assumed to have a package accessibility, which is actually pretty much the same as a public, but it's not explicitly the same. It's a different access modifier from a package level. I believe by default, I think the method itself would be private, but don't quote me on that. I believe data is private by default, public if you make it public. So I would assume that the same rules would work with a method, but that's an assumption. So if the class leaves any of the methods of the interface undefined, the class becomes abstract and must be declared as abstract. So we decided to create the employee class, and we're extending whatever we want, because we can also extend as well as implement. We're going to implement comparable, but we've decided we're not going to put we're going to put a method in there, but we're not going to implement compare to, which is in the interface comparable. Then we've just created an abstract class. And because it's abstract method that's in this class, we have to make the class abstract. So now we took an interface, implemented it in a class, and created an abstract class out of it, which is okay. It just means that this abstract class is going to be inherited by another class that's going to implement the interface. Otherwise, we would have implemented the interface in this class. So if you're following the logic, we can take a base, yeah?
Even for that, inverted classes, we have to write implements comparable.
Nope. We just extend the class. Yeah. We've created an abstract class, essentially. And we can inherit from an abstract class and not just say, create my new class extends my abstract class. And we don't have to include the interface again, because we've already implemented the interface in the abstract class. Well, we haven't implemented it. That's why it's abstract. If we implement it, we don't have to make the class abstract. So we can create an abstract class automatically by implementing an interface and not implementing it. When we implement an interface, the rule is you have to implement all of the methods that are in that interface. If you don't implement one of the methods, then you're stuck. It's incomplete. And abstract classes are incomplete classes. They're classes that have methods that aren't implemented because it's waiting for a future. It's waiting for a future implementation. So in the future, somebody else is going to build on that class and make that abstract class real instead of leaving it abstract. Eventually, that abstract class is going to be included in something, because you can't make an instance of an abstract class. So, and that's about as tricky as it gets. It doesn't get any trickier than that. That is the entire concept, actually. So if you can kind of catch the logic with what's happening and how it turns into an abstract class, you're done, pretty much. So you can use interfaces to a high level of expertise at this point, if you followed that. It takes a couple practice. I have some examples as well, so I'll show you some examples with it. So a single class can implement multiple interfaces. Just separate the interfaces by a comma. So we have class employee implements comparable, comma clonable, comma whatever we want. And going back to what I said in the beginning, that's how we get multiple inheritance. We get the ability of one class to implement hundreds of different interfaces, and it only extends one class, but we can implement as many as we want in terms of the interfaces. And the interfaces are abstract classes in theory, but they're not called abstract classes, they're called interfaces. And one of the biggest differences, though, in an abstract class, you don't necessarily have named constants for data. You could have data that's not final, that's not static. You can have public data, or private data. You can have different varieties of different data members in an abstract class. Normally, you don't have very much data in an abstract class. Why would you have that if it's abstract? You're going to implement it. So, to instantiate properties of the interface. Interfaces are not classes, so you can never use the new operator to instantiate an interface. So public interface comparable. Comparable x is equal to new comparable. No, can't make a new object this x here, this x is a reference. This is a reference variable, actually. So I can say, I can still declare the interface variables. This is okay, I can say comparable x, because it's a reference object or reference variable that's going to refer to an object. We can assign x is going to be equal to something in the next line or so. And I can make one of type comparable, which is of an interface type reference. And because of inheritance, an interface type reference can equal to an object that implements the interface. And now the tongue twister continues. So if I said comparable x, I can't say new interface because that's an interface. There's no functionality in it. But it can refer to an object of the class that implements the interface. If employee implements comparable, I can go x is equal to new employee. That actually works. And x is of type comparable, which is the interface type, which means we've got a reference to an object of an interface that is equal to an instance of an object that implements the interface. So let's go back. Did I do inheritance last week? I've done inheritance in this class. Some people are going yes, some people are going no. When I did inheritance, I probably should have told you that inherited objects have multiple identities. So a person who gets, we have a person base class, and then we create an employee and extends person, and then we create a teacher that extends employee, and then we create a janitor that extends employee. The janitor is a janitor. He's an employee, and he's also a person. And the teacher is a teacher and an employee and also a person. If we had anything below that, like object, it would also be an object. They're both objects. So we can actually treat the employee and the janitor as objects, and they would be equal because they're objects. All objects, we would be able to use them as if they were all of the same data type. So an employee in this case that implements comparable also includes a comparable interface. So that's equal to a comparable interface. So now we have the object equal to a comparable interface. The reference of it as an interface treats it like an interface, which means only the functionality that's implemented in the interface would be available through the referenced object. We'd have to typecast it back to an employee and assign it to an employee reference object if we wanted to treat it like an employee. Here we're going to treat it like an interface. What's in the interface? We only have one method, compare to. So if we wanted to compare two employees to see, are they both teachers? Are they both janitors? We could do this and use the compare to object that's in comparable interface that's been implemented in employee. And when we created this comparable x, we created an object that was of reference type of the interface that included the compare to object, method to be performed on that object. We can compare two employees, essentially, which is all the functionality we have in that interface. So we can take two employees and go, are you both teachers? They come back false, because one's a teacher, one's a janitor. So we can use it for that purpose, essentially. Or you could typecast it as, I shouldn't say the word typecast. Morph the object back into an employee. Instead of treating it like an interface, we can treat it like an employee by putting an employee, using it in the future, taking X and putting employee in the brackets and converting the object and assigning it to an employee reference instead of a comparable reference if we wanted to use it further down the road. We're not stuck. Just because we've created a new employee. We have never created a new interface. But when we created a new employee, we're referencing it as an interface object. So we would have to change the reference if we were going to use X, which is an interface object. Is what I'm saying. We'd have to actually create employee barb equals X. Or equals, well, actually, yeah, equals X, and then X is an interface, so we'd have to go employee into brackets, inside of brackets, to say, cast you X as an employee instead of an interface. Have you equal to employee barb or something. Which would be a way of would be a way of changing the identity. And that comes in handy, because then you can take all your objects in your entire program, treat them as objects, treat them as employees, treat them as people, which is what you're doing in that second programming assignment, actually. And then going through, you can scroll through them, send them back and forth to methods and stuff like that, and then treat them as other things that they might happen to be. And that's actually the polymorphic behavior that's going on in terms of the feature. You want to put a label on it. Extending interfaces. Interfaces support multiple inheritance, and an interface can extend more than one interface. So super interfaces and sub interfaces exist, just like classes do. So public interface, serializable, extends, serializable, runnable, other interfaces. So just the same as we have with classes, we have interfaces that support multiple inherited interfaces, because interfaces have multiple everything. In a class, we can extend multiple interfaces. In an interface, we can implement multiple interfaces in a class. We can inherit by using the keyword and extend multiple interfaces in an interface, because we're using an interface here. So interfaces break the rules of single line inheritance. If you just remember that and just go anything having to do with an interface, multiple everything is possible. So it allows us to kind of break that this class extends this class, which extends this class, which extends this class formality, and say, oh, if we add interfaces in there, then we have multiple everything if we want. So, and it brings out the multiple class inheritance by default, because instead of inheriting from abstract classes, we're implementing interfaces instead of abstract classes. So in terms of extending interfaces, a little word about the constants, the named constants identified in the beginning. An extended interface inherits all of the constants from its super interfaces. So all of those variables that we defined up front, those public, static, final, named constants variables are all inherited in all of the other interfaces, which comes in handy. So take care when sub-interfaces inherits more than one constant with the same name. Could have a problem. Or the sub-interface and the super interface contain constants with the same name. Always use sufficient enough information to refer to the target constant. This is what I'm talking about for those of you who may have come in a little later. These are by default when you have data members that you've defined inside of an interface. They are of type public, static, final, which gives them the equivalence of what we'd call in C++, we'd call it a named constant. They're constant characters. And by default, we also put them in capital letters to remind ourselves that they're constants. Well, if we take multiple interfaces and we inherit them in an interface, we might have multiple silences. We're going to be confused, where there's ambiguity that's created because we don't know which one are we talking about. So we have to reference it by a dot notation, essentially. Let me go back to the slide where I was at. And here it is. Here's a tedious detail. When an interface inherits two or more constants with the same name, in the sub-interface, explicitly use the super interface's name to refer to the constants of that super interface. So here we have A, we have interface A, interface B, and we both have value 1 in here, which comes up if you use the same names for all of your variables and all of your constants, and they're all included. Extends A and B. We have A dot value, B dot value. So we use the name of the interface along with the name of the variable to differentiate between this value and this value, which both have the same name. Actually, this is the same logic you would use in any other case. In regular class inheritance, if you rename and you have this isn't a name constant, but if you have another public data member that you've inherited and you've used the same name, you've overwritten it. It's going to use the last implemented the last changed copy of that variable. Interfaces, it's going to include all of the interfaces. So the regular rules that we have when we inherit one class from another, we overwrite or overload. Interfaces, we include everything, which is kind of different logic. So we've actually included both values if we've used both this two interfaces in our implementation. Yeah?
Here A and B are interfaces, right?
Mm-hmm. Interface C extends A and B.
You can use the extended word. It's like you're writing like implements A and B.
Ah, because we're creating an interface that is extending two other interfaces. We're not creating any classes yet. Because extend inherits a class from a class. Extend also allows interfaces to inherit from other interfaces.
So if we are implementing only, if you are like implementing in a class, then you use the implements keyword.
Correct. If you're this is creating an interface C.
And you use extend.
Yeah, because I'm creating an interface C that's inheriting from interface A and interface B. I'm not implementing the interface, I'm extending the interface, which means I'm inheriting. So in inheritance, you always see the keyword extends, and we can inherit interfaces in interfaces, and we can actually support multiple interface inheritance with interfaces. In a class, we extend only one class, and we go comma implements, which is where we use the word implement, is at a class level to implement an interface. Here, I don't know why, normally we would just put A and B together. But if we actually had two different interfaces that were both using value, I would have probably just said A value and B value here for the classes, you know, in the hopes of not having to run into this problem in the future.
There are methods in interface A and interface B.
Yep. So in this particular example, what it's showing is that,
Override them.
yeah, no, not override. You'd have to use the same thing. If you were running a named constant or a method, you have to say, well, what interface are you talking about? Interface A or interface B? If you have named them the same. Hopefully you're not going to name everything the same, which is what I was saying.
Then you don't need to use the interface.
Yeah, if they're different, you don't have to because it's all included. It's not like taking a cut and paste and saying, here, we're going to give you all this stuff, we're going to give you all that stuff. Well, sometimes we have some duplicates. And then how are we going to know the duplicates? Well, we have to refer it to, do you mean that method or that variable that's inside of A, or do you mean the one that's inside of B? And that's where we go A.value or B.value.
So for the methods, like if there is another class which implements the interface C, you can directly use them.
Yeah.
You don't need to say A or B.
No, if it's, you only have to say A or B if it matches. Yeah, if they're the same. Otherwise, we don't know the difference between value and value.
Can we override, like suppose if A has some method and then can we override the same method in the class?
In a class implementation, you can.
Yeah, interface C.
In the interface, you can by not. Well, good question. You're implementing the interface, so you're hiding it when you redefine it. And actually, this is a reason why I went to the next slide, is because essentially what we're going to do now is take a super interface and a sub interface that contains two constants with the same name, and one belonging to the super interface is hidden, and the sub interface one is going to be available. It's there, but it's hidden. So you've essentially overwritten it. Because, well, you haven't overwritten it, though. You can still get at it. But it's hidden.
Use the interface name and then maybe.
Yep, that's how you do it. So in the sub interface, you access the sub interface's version of the contents by directly using its name. In accessing the super interface version constants by using the super interface name, followed by a dot. So here, x.value. But if we don't say, if we have value 1, value 2, we've implemented a new interface. We've included both the super, when we've inherited one interface from another interface, the super interface is always going to be the one that's being used first. If you want to go back, we've got to say, go back there. You've got to explicitly say, go back to the previous class and use it from there. Otherwise, it's hidden. It's not visible. Which is answering your question, I think, hopefully. Yeah, which is what's the next slide I was trying to get to it. So, outside of the subinterface and the interface itself, you can access both of the constants by explicitly giving the interface name. That's this example right here. So let's say we were in C and we wanted to use it. We're going to use what we've implemented in C, whether or not it's in A or B. So we have interface X, and interface X has value equals 1. Interface Y extends X. Value now equals 2. Value is going to be equal to, this value up here is now hidden. It's still there. We can go x dot value down here. But this value and this value are now different. Because we took it and we implemented with the new value. And so for all of y's, we have value is equal to 2. For all of x's, we have now, it's still 1. But it's hidden from view. So if we just said a value, print out value, we're going to get the y's value. That's going to print out and not x's value, which is essentially overwriting, if you want to think of it that way. But it's really hiding it, because it's still available. It's not completely overridden. Not like in the cases of classes that inherit and actually overwrite. We can't go back. We have to take whatever we've overwritten it with. In an interface, we still have it built. We still have all of it. So, all right. So outside the interfaces and the sub-interfaces, you can get at it through the name. Here's an example in the previous example. Actually, this is just describing what I just described a few minutes ago in terms of the x and the y. Okay, so when the super interface and a sub-interface contain two constants with the same name, and the class implements the sub-interface, the class inherits the sub-interface version, obviously, of the constants, as its static fields. Their access follows the rule of the class's static fields access. So class Z implements Y. Inside of the class, system out z dot value, and the value is equal to 2 because it's implementing Y. And then we have z dot value, z dot value, z dot value. It's also going to be equal to 2. So the class itself, the access follows the rule of the class's static field. So it's from a class level. Once we've implemented in a class, the behavior is from the class. Object reference can be used to access the constants. So the sub-interface version constants are accessed by using the object reference referred to in the dot notation, as we've seen before with the constant's name. As we saw in the previous example, they're accessed by explicitly casting it. So here's an example. We have zv, z is a v, is equal to new z. So we created a z from a v, calling it v, but it's a z. System out v dot value, printing it to the screen. Now we have y. This is what I was talking about in terms of casting it. Treat the z like a y, and then print out that value. Because if you go back to inheritance, if we have y that inherits, so in this case we have z that implements y, there's a y inside of each one of the z's. Just the same way as we took in this previous example and we said one of these did inheritance. And we have an a and a b inside of c. We have them both. When we take a class, we have them both. A employee is still, a janitor is still an employee, just like the way a faculty or instructor, teacher was an employee. Can't remember what I called the object. They're all people. And if they have interfaces in there, they're all the interfaces as well. So we can cast it to make it into a y, and then go dot value and get the y dot value. Or we can make it into an x dot value. So depending upon whether we want to treat it like a y or we want to treat it like an x, we can get the value from the object that we've created, from the instances of those objects. And this is not really typecasting, it's object reference casting. It's taking the object and saying, I know you have all these other objects inside of you. Let me see your employee object. Let me see that value that's associated with that one versus your staff object or something. So, extending interfaces. Let's talk about the methods for a little bit here. So, talked about the data previously. If a declared method in a sub-interface has the same signature, there's that word signature again, I'm never going to forget it, as an inherited method and the same return type, then the new declaration overrides, to answer your question about methods, overrides the inherited method in its super interface. So it will override it. Anytime you ever have, and this is probably the most consistent rule, anytime you always have the same name, you're going to override it. Interfaces, it's kind of different because it's not really overridden, it's hidden, we can still go back to it. But in classes, for general, and we're overriding it if it's the same. So it overrides the inherited methods and its interfaces. If the only difference is the return type, then there is a compile time error because it doesn't know how to do it. It doesn't know what to do. So it doesn't treat data members the same as member functions. Member functions are overridden, data members are hidden, because the data members are needed for the implementations of the member functions, and they're of a slightly different nature for the use. And we are going to get, if we're going to get a compile time error, it won't allow anything outside of an override. We can't complement, can't overload it. So an interface can inherit more than one method with the same signature and return type. The class can implement the different interfaces containing the method in the same signature and the same return type. Overriding. In interfaces has no question of ambiguity. The real behavior is ultimately decided by the implementation of the class implementing them, which is kind of interesting. So the real issue is whether or not a single implementation can honor all of the contracts implied by the methods in the different interfaces. And methods with the same name but different parameter lists are overloaded. So it's really, not to put this down, it's really the same as inheritance with classes. It's treated in a similar fashion with interfaces. So it has different parameter lists. If it has different return types, you're going to get a compile time error. If it's the same return type, it's going to be overridden. If it's different parameter list, same return type, you're going to get an overloading and overriding. And when you overload, you're almost just replacing it because you're making it hidden. When you're overwriting, you're making it hidden, so you're practically replacing it. Why use interfaces? And that, in a nutshell, I kind of gave it to you already. But here's an example. I put this out on the website, actually. We have shape, point cylinder, point circle, and cylinder that come from point. And then we have test.java. So the usefulness of interfaces goes far beyond the simplicity of publishing protocols for other programmers. Because, when you put together an interface, what you're doing is you're putting together a template saying, build this stuff into the class. And if you don't implement these methods, you're going to have an abstract class because it's not done yet. So any object of a class that implements the interface may be passed as an argument. So it makes it adds to the polymorphic behavior as well. If we've implemented interfaces, we can use it at the interface level. So gives us a little bit more object behavior. So let's talk a slight different tangent, and something you may or may never actually run into in your programming career, but marker interfaces and object cloning, which is kind of takes it to the next level here. So a marker is a tagging system to tag something. Interface has neither methods nor constants. Its only purpose is to allow the use of the instance of in a type inquiry. So as we saw before, when we took a look at that object employee and we assigned it to an interface comparable, and it had one compare to method in there. What if it had nothing? It doesn't have to have anything in there. Then we've created what's called a marker interface. We've stamped a label on somebody, and we said you're of this object type. We have added no functionality, and we've given you absolutely nothing that makes you any special than anybody else outside of this label that we've stuck on you. So we can treat you as let's say we stuck an ITU label on you. As students, we implemented the ITU interface, and the ITU interface had nothing in it. It's completely empty. No methods, no constants, nothing. It was just a blank interface. Then we can go through all of the objects that we've created and say, okay, how many of you are from ITU? And identify you by your interface. It's a marker. We've stamped an ITU label on you. So we stuck you guys out in a room full of other students, and we say, okay, it's like that Wii game, when you round them up. Okay, guys, what do they call the Wii characters? You guys play Wii? There's the Mii's. No, you create a Mii, but what was it called? Those characters, those avatar characters or whatever, avatars or whatever. There's a button that says round them up. So I press the round up button on the students that are in the room, this hall of thousands of students, and all the ITU people go over here, and all the other people go over there, because they're tagged. You have a label on you that says you're from ITU. The label is written in your object, and your object is marked by this blank interface that we've used. So it's a way of marking objects to say you all belong over here, you all belong. It's identification, essentially. So you can tag the object. You can't tag it with a serial number. That you'd have to use a class variable for that. You'd have to use a class, a static number to put an ID on you for all of the instances that belong to that particular class. But in terms of rounding up all the objects and identifying them, the marker is the tagging system that you're going to use for that. It's a quick, easy way to tag objects. Why would you want to tag objects? Well, because if you want to say, are you an instance of ITU? We can find all the ITU objects if we needed to, and find all the other ITU objects, the transfer states, and organize the objects a little bit better. We also have what's called a clonable interface, and that's an example. We can clone you by adding the interface. So we've cloned ITU objects by making more ITU objects by including the interface in every one of those objects that we've created. Object clone, what's an object clone? An object clone and clonable interface is such an example in terms of what we looked at previously. That's what I meant to say on that. We have a different concept called an object clone that we can create as a separate concept than marker interfaces. A clone method returns a new object whose initial state is a copy of the current state of the object for which the clone was invoked. Subsequently, changes the new object clone should not affect the state of the original object. So you guys see that movie Multiplicity? The guy is an overworked construction worker, I think. This is an old movie. If you haven't seen it, rent it. It's hilarious. So on your next rainy day, go to Redbox or wherever you get your videos from these days and get Multiplicity if you haven't seen it yet. And you'll understand object-oriented programming from that movie. You'll understand cloning. So the guy's overworked. He says, man, I wish there was just 5 of me. That way I could get everything done I needed to get done and still spend time with my family. So he makes copies, photocopies of himself with a cloning machine. So he's got clone number 1, 2, 3, 4. Only problem is with all the successive, what do you call it? The next, which each consecutive clone, that's the word I wanted, it's a little deteriorated. It's not quite as good as the original. It's kind of like when you take a photocopy and you take a photocopy of the photocopy and a photocopy. Eventually that image is pretty bad. You want to start with the original because you only get a copy of the original. And then his problem was he made copies of copies. He cloned, some of his clones made copies of themselves, but they started degrading because the clones would change. And it's kind of the interesting thing because each one of the clones changed to different parts of his personality. So they had a funny one, they had an upset, angry, stressed out one, they had an easygoing one. Every one of his duplicates was slightly different, and that was what made the movie funny because it was like, it really is all the same person, but it was all the different sides of his personality. Long story short, he had to destroy the clones in the end. It was clone death because he decided he was better than all the rest of the clones. The combination of all of him put together was better than the clones. That's the moral of the story, I guess. But long story short, you only get a copy of the current state of the object. And so once you create the clone and the clone changes, the object changes, you can't go back to the original anymore. It's modified. So if you make a copy of the modified clone, you're getting not the original clone, you're getting a modification. So in the object-oriented world, we can create clones, 3 factors in writing a clone method. We can write a method to clone an object. The empty clonable interface. So you must implement it to provide a clone method that can be used to clone an object. So you create a clonable interface, and you make the interface, you use the interface in the new object that you're creating. And the clone method implemented by the object class performs a simple clone by copying all of the fields of the original object to the new object. Essentially, you're just copying all of the fields. So all of the data is identical. And then the clone not supported exception, which can be used to signal that the class's clone method shouldn't have been invoked. So you can prevent bad clones from being created if some of the data is not assigned, if some of the data is not copyable, if it's protected in some sort. So we can create bad clones. We can prevent bad clones from being created by using some exception handling. The object class provides a method named clone, which performs a simple clone by copying all the fields of the original data to the new object, and it works for many classes but may need to be overridden for special purposes. Especially when you want the clone to use dynamically allocated memory instead of statically allocated memory, or in some cases in which you want the clone to be changed and you don't want it to have everything that the original had. So, shallow versus deep cloning, and that's essentially working with the dynamically allocated memory. So shallow cloning is simple field-by-field copy, which might be wrong if there are duplicates of the references of objects that shouldn't be shared. If one clone has created some memory that it is using, you don't want the other clone to reference that same piece of memory that the original clone is using. Because then instead of clones, you got two people working together, two objects working together with the same piece of memory. So you take the memory that's being referenced and you make a copy of it. That's a deep copy. So shallow copy is just the non-referenced memory, but the information that belongs to the object that is being copied. A deep copy is any referenced memory that the object might be using. If the object had another object inside of it that was referencing something, or if it was referencing memory, taking and making a physical copy of that as well. So it's at a different memory location, so it has its own copy of it, which is the same as shallow and deep copying, and you get in C++ with a copy constructor. But we don't have a copy constructor in Java. We don't need one, actually. But when we make a clone, we have to deal with that kind of concept, copying reference data. You're never, probably ever going to make a clone. Who knows? That's a good idea. That's a good question. Well, when you want to try something out temporarily on an object but you don't want to use the original, you can make a clone of an object to experiment, and then if you destroy the object, no problem, I got the original. Go back to the original. Different than cloning in the real world, I guess. You could possibly make a multiplicity example out of it. A shallow copy copies just the information that belongs to the object that is part of the object space in terms of its original object space. If an object is referencing memory somewhere else, it has some communication going on with a piece of memory that it's referencing. A deep copy also makes a copy of all referenced memory that might be associated with that object. Otherwise, if you take an object and you clone it, and this object's dealing with this piece of memory over here, then this one's going to be dealing with that piece of memory too. The same reference is created for both objects, which is kind of the concept of a linked list. It's not a linked list, but pointers in C++. We got two pointers going to the same memory location, and in pointers you make a shallow or deep. You make a deep copy when you pass an object to a function or a method, and you're treating it by reference, and you don't want it to. You want to treat it by value instead of by reference. You make a copy of that referenced memory, and you put that in a copy constructor so that the object will take care of itself by value instead of by reference. But in C++, you have to do that all manually in most cases. In Java, you only have to do it manually when you're cloning. When you're going to clone, let's say you're a construction worker and you need five of you to get all the work done. So you don't have to be so stressed. Then you can clone yourself 5 times, and those objects can do all the work. And then the original object can be freed up to go to the beach and go on vacation or something. And who knows, maybe you're creating a multi-threaded application, and you want all those clones to be doing all that work, because one object is working too hard. I don't know, it makes sense for passing it, I think. You can pass a clone to a function. I would use it, it's actually kind of, that's why I originally started out saying you're never going to clone, probably. it's part of the language, something I should tell you about. It's kind of interesting when you think about the capabilities, but I don't know if you're ever going to use it. You may not. Interfaces you'll use. Marker interfaces you'll use. Cloning you could use. There's some rare cases in which you might want to clone an object. In the case of making some temporary object to go play with or to do something with, makes sense. It's just like the real object. But you make a clone of it so you can destroy the clone. If that happens, you don't destroy the real one. So. And here's the original and then the copy that's being created. Deep cloning, you don't have to worry about the rest of this lecture actually. The concept of cloning an object is what I wanted to present to you. You're not responsible for creating deep and shallow copies, and you don't actually have to do any cloning in this class either, so none of the assignments are going to require any cloning. But I thought I would mention the concept too. So you can skip slide 18, which is this is going to go into a deep copy versus a shallow copy. This is the shallow clone copy. The deep clone copy, don't worry about the examples, what I'm trying to tell you, is you're basically making two separate copies of the memory. And then you can, this copy is using this one, this original is using this one. In the shallow example, they're both referencing the same shared memory. So you're just making another copy of the same referenced memory and putting it at a different memory location so that the copy isn't going back to the original. See if you decide that the class needs a deep cloning, not the default shallow copy cloning, which is the default that happens. Then the class must implement a clonable interface. So instead of having a copy constructor, we have an interface for that. And we interface with clonable if we were to implement this, which you don't have to do. And clonable interface has no methods, no constants, but it's a marker. So it marks a class as partaking in a cloning mechanism. So it uses a marker class to say, you're a cloned object. Oh, okay, so you're like that one over there. So then it gives them a new identity as a clone instead of as an original. So you redefine the clone method with the public access modifier. And if you decide that the clone just needs shallow copying, then you would still need to implement the clonable interface, redefine clone to public, and then add a super.clone. Go back to the super interface. Go back to the clone. Don't worry about it. In terms of the implementation details, because you'll probably never create a clonable object. Who knows, you might. We'll see. Interfaces and abstract classes. Why bother introducing two concepts, abstract classes and interfaces? Abstract class comparable. That's what we learned last week, where we have an abstract method compare to that is of int, integer as the return type. And then we have class employee that extends comparable. This is last week. And this week, we see public interface. I don't know if this was last week or the week before. I don't know. It was one of the previous lectures when I talked about abstract classes. Now we got public interface comparable. They look the same, except for this isn't a class, it's an interface. It has the same method, but we can leave this stuff out. We can also put it in if we want, and we're not going to get an error. But by default, if we change it to something else, we're going to get an error. By default, if we leave it out, we're going to get this public abstract. Is how it's going to be defined, because all interfaces by default, all the methods are public and abstract. And it's going to implement, here we have employee that implements instead of extends. So the difference is with the implementation. This is kind of the conclusion or the review of the concept. A class can only extend a single abstract class, but it can implement as many interfaces as it wants. So the selling point for interfaces is the multiple interface inclusion, where if we're creating abstract classes, we can only extend one abstract class from one abstract class. So people argue and they say, no, Java is only single line inheritance. It's multiple line inheritance. If you consider interfaces. If you haven't learned interfaces yet, you might think the language only goes single line. Only goes from one class to another class. And you compare that with C++, and you go, well, C++ supports multiple classes to be implemented, but they don't have interfaces. So it's just, in fact, most people would argue and say that object-oriented programming as implemented in Java is more true to the form. It's true object orientation, follows more of the standard behavior, what we would expect, and C++ is kind of a half-done implementation of the same concept. But to give C++ credit, they came out first. Yeah, naturally. If you take a language that's already done and you dissect it and you rebuild it from scratch, you're going to do a better job. And if you haven't noticed, Java is nothing more than that. It's C++ taken apart, dissected, fixed, more consistent, follows the same syntax practically, the same programming language practically. So if you know C++, you can pick up Java quite easily. If you've learned C++ as your first object-oriented language, you probably didn't learn everything there was to know about object orientation. If you learn Java as the first language, you're learning more about object orientation than you'll ever really actually kind of visually see from C++. Also taken into consideration, there's a good percentage of C++ programmers who've never programmed in object-oriented fashion. Yet they've been using C++ for years. You can't do that in Java. You have to follow object-oriented programming methodology in Java. You can't create a function in Java. It's a method in a class. Everything's a class. In C++, you can have a main, and you can have function here, and function here, and function here, and never create a class, and never program in any object-oriented fashion at all. And still consider yourself a C++ object-oriented programmer. I don't know how that works, but apparently it's possible. Alright, so abstract classes can have multiple implementations, protected parts, static methods, and so on. While interfaces are limited to public constants, that is true, and public methods with no implementation. We can't put an implementation in an interface. It's just not possible. We can put an implementation in an abstract class. We can have an abstract class that has some abstract methods and some non-abstract methods, and then when we inherit that, we get everything. So it doesn't mean we have to have everything abstract. It just means that if an abstract class only has one abstract method in it, that's the minimum. If we take that abstract method out, we no longer have an abstract class. We can put it back to a regular class. It doesn't have to be abstract. So. Alright, that is everything I ever wanted to know about interfaces for today. And I have out here on the website, I believe, let me just check this actually, in the course materials directory, I've got that shape. I should have that. Now here's the shape, the point, the circle, the cylinder. And the shape is an interface. So it's an interface shape, and it has a calculation for area, for volume, returns the shape name, get name. And in the interface you might notice I actually put in public abstract double. I could take that out and it would be just fine. I could just say abstract, it could just say double area, double volume, string, and it's known already to be public and abstract. From that, I can create a point, and we can see that the public class point extends object, and it implements shape. And in here I can have protected methods, x and y, coordinates for the points. And in here I'm going to have the area, and I'm going to have, get y, get x, but I'm also going to have an area, volume, and get name. I'm going to implement those methods that I've put into the interface, and then from point I can have from circle that also extends. So I can have public class circle that extends point, so inherits from point, the protected methods. But every one of the circles that I create is also a shape. And answering your question again, you don't have to keep implementing shape all over again. Shape is already implemented in point, and point is in circle. So they're all of the same object line, all the same inheritance line, and with the same implementations of the interfaces. Because once we include an interface in there, it's there, which is how those marker interfaces work. So you could just put a marker interface in there too if you wanted to on top of that. You can implement as many, and you don't have to implement a marker interface, it's just there. And we're just adding to it to make a circle that extends a point. We didn't have to do it. No, we didn't have to extend a point for our circle, but no, we could have. And then there's the cylinder, and the cylinder extends the circle. So if you want a good inheritance example that uses interfaces that's what this example is all about. It kind of gives you that entire, and we'll throw an interface in here, and we'll extend this one, we'll extend that one. And this is actually going up pretty, this is going from a cylinder, circle, point, shape. So it's pretty deep in terms of its inheritance. So. And every one of these has a area, volume, and a print function, because the area of a circle is going to be different than the area of a of a cylinder, or the area of a whatever. So all of the areas are going to be overridden. So, and I'm trying to think. Nope, that's it for the examples. I could spend time going through the examples, but instead I'd rather have you actually download the examples and experiment with them on your own. Questions, comments, concerns about interfaces? New? And then that's good. We're done for today. Okay, good. Make sure to sign the roster if you haven't. There's a roster going around actually in my video.